I can't hear you, Harry. Can anybody else?
He's not talking.
I thought he was. Thought it was his mouth moving. Okay.
Well, if his mouth is moving, it doesn't necessarily mean he's lying, like in some other cases.
That's true.
Oh, I'm sorry. I didn't turn the audio on.
I was right, Jim. I was right. His mouth was moving.
Aha! But in a Lorentz transform, would the mouth be a different size, or would it occur at a different time? That's a big question there.
What are you saying?
Could be contracted.
Oh, just some humor. Intended humor.
All right, I'm going to talk a little bit about radio astronomy because we kind of talked about this plasma thing, and that kind of came up. I had this idea of because I'm a satellite engineer, this is kind of a topic dear to my heart. And I'm also a ham radio operator, I'm going to mention that. And this is also a topic that turns out that hams have been struggling with for a long time, and that is noise. And so what is radio astronomy? Is doing astronomy with radio waves, but the radio waves are noise. They're not transmissions with information attached to them, which we call modulation. They're noise. And noise is any unwanted source of EM radio wave energy that interferes with transmission of information. That's the way we talk about it. And there's lots of noise coming from computers, and nowadays it comes from refrigerators and vacuum cleaners and all kinds of stuff like that. And radio astronomy deals with noise that can be said to contain information. Okay, so what kind of information does noise contain? And what is measured or detected is the noise power received by a radio telescope antenna. So we have what's called a radio telescope antenna. It points at an object that gets noise, and that noise somehow contains some information. And so I'm going to talk a little bit about radio astronomy as the art of converting noise into useful information. Okay, so what kind of information can the noise tell us? Well, if we know that it's coming from a particular place, we get the source of the noise. Where is the noise coming from? Well, we can identify. And ham radio, usually it's the guy next door running a machine that's noisy or something. Okay, the other issue of what can the noise tell us? The spectrum of the noise. How does the noise change with frequency? That's another piece of information that can be extracted. What is the power, the energy of the noise, and how intense is it? These are information that radio astronomers use and collect. What is the shape and size of the source of the noise? What's it look like in the sky? Is it big? Is it small? That sort of thing. And here's the important thing. What are the different types of sources of this radio noise? And that's really the ultimate question that radio astronomers are dealing with. Okay, so let's do a little bit of the history. And Carl Jansky was working for the Bell system, and Bell Laboratories, it's called Bell Laboratories now, in Homedale, New Jersey. And they were working on shortwave telephone circuits, transmitting telephone via shortwave. And he was investigating noise that could be picked up by a receiving antenna for such circuits. And he identified that one of the sources of noise was coming from the center of the Milky Way galaxy. And that's kind of interesting. He was using a directional antenna and was able to notice that when the center of the Milky Way passed in the beam of the antenna, that the noise level was increased, and therefore he was able to identify the source of the noise as coming from the Milky Way galaxy. So the Milky Way galaxy, there's radio noise that's detected that comes from the galaxy that the Earth, our sun, exists in. Later, Reber, who is a ham radio operator, and this guy's really impressive. Basically, with his own money, built a radio telescope, and he was able by 1940 to make a map of this radiation, this noise coming from the Milky Way. And then during World War II is kind of important because there's a big emphasis. The British were pioneers in radar, okay? And the radar became very important to the British defense during World War II. And there's a very interesting story. I don't know if people are interested in military history. I'm interested in World War II military history. But there's an event called the Channel Dash where the Germans had battleship, the Gneisenau, and cruiser Prince Eugen, and some other ships. And they were in Brest, France. And they wanted to move them closer to Germany. And so the Germans moved the ships. And the British wanted to destroy the ships as they passed through the English Channel. And this operation turned out to be a complete fiasco. The British failed to destroy the German battleships. And because of this, Churchill ordered an investigation. I mean, when Churchill ordered an investigation, you can believe that people were looking for some explanation as to why this operation failed. And one of the results of this investigation was they discovered that the British radars didn't work properly because they were receiving noise interference from the sun. And this was the first time that any noise or radio emission had been detected from the sun, which I think is kind of interesting. The British thought that the Germans had invented some kind of sophisticated radar jamming system, but that wasn't the case. Okay, so after this, the people who had worked in the gentleman who made this discovery that the radars were being interfered with by the sun, he became interested in radio astronomy and studying the sun. So there was a lot of equipment available, surplus radars, antennas, and that sort of thing. So there was a very great interest in this problem of extragalactic noise. Here's more on Jansky, and I'm not going to go into the detail. If it was a longer presentation, I would. One thing, I always wondered, if you see these pictures of Carl Jansky with his antenna, what kind of an antenna is that? And I did some research on this because I'm a engineer, electrical engineer. I found this something called a Bruce array, which was something I'd never heard of, so I learned something about that. Okay, Reber actually, this is kind of interesting. Reber uses the term cosmic static, which is kind of an old-fashioned term. Some people call noise static, and so his reports are talked about cosmic static, which really is just another term for noise. And in 1940, he did his first report. Now he basically had his telescope. He made chart recordings, okay, measuring the power of the noise, and when the Milky Way would pass through the beam of his antenna, this would be recorded on a chart recorder as an increase in the level of the noise. And he published his first map in 1944 and he was using 160 megahertz. And then and this talks about a couple of the papers that he reported. Okay, I talked a little bit about this, the post-war heyday for radio and radar astronomy. And they were making, this was really a period in which, if you were a radio astronomer, you were making discoveries practically every day. And it was very fruitful. They were doing, detecting, they discovered that sunspots radiated, solar storms created radio emission. There was people who were doing moon bouncing radar signals off the moon. When I went to college, they had what they called a meteor trails station where they had a radar that would detect when a meteor passed by because it would create an ionization trail in the ionosphere. And so there's a lot of studies of meteors that were done. The 1946, the first solar flares detected. Now this is where we get to the important stuff here. In 1948, while people are making these maps, they discovered what they called radio stars, which were discrete point sources, or appeared to be point sources of intense radiation. And so the idea was that these were radio stars. Turned out that's not the case. And this one Cygnus A, which is very important, was discovered in 1948 or detected in 1948. And by 1950, there were many of these discrete radio sources or radio stars had been identified. Okay, now we're going to shift to the 1950s was when really a lot of the very early and important work was done on extragalactic radio astronomy. And that had to do with, and I'm going to talk about this more later, the identification of these so-called radio stars. Many of them actually turned out to be external galaxies. And that's really what I'm going to try to focus on here. Okay, another development in the early 1950s was neutral hydrogen emission. Neutral hydrogen in the galaxy emits radio waves, and they were able to map out the location of these sources of noise. And from that, they were able to map out the structure of the Milky Way galaxy. That's pretty important. Also, in the early 1950s, they determined that this discrete source, Cygnus A, had two sources, so it was a double source. More about that. It's kind of amazing they were able to do this in the early 1950s. And then, of course, we had they were making catalogs of radio sources, and so the first catalogs came out. Okay, in the 1960s, there's a big improvement in technology that occurs. There was a discovery of the cosmic microwave background radiation. I've talked about that. They discovered quasi-stellar objects, quasars. I'm not going to talk a whole lot about that. They're related to radio galaxies. And then, of course, by the 1960s, there was the recognition that radio galaxies are double. They have this double structure. And the technology improves to the point where you can make radio maps. Okay, I'm going to shift gears here now. And I'm going to talk about Cygnus A, which I think is kind of interesting. It's interesting. It's 760 million light years away, and it's the second brightest discrete radio source. Okay, so imagine this. This thing's the second brightest source of radio waves in the sky, and it's 760 million light years away. It's just an amazing, it's stunningly energy, produces an amazing amount of radio energy. And looks like, if you look at the maps, I'm going to show you the map. Here's the map. Reber made this map in 1944, and you can sort of see it here where I'm moving around here. This is his map of the Milky Way. It's kind of unclear to me how accurate his map is. I don't think his map is very accurate if you look at more accurate maps that are made later, but it looks like he was able to detect Cygnus A. It's a very powerful radio source. And one of the things that's curious was when they tried to identify what this source of radio energy, of noise is, there's nothing there. And, it's in a place in the sky where there's nothing to be the source of it. And it wasn't until 1954 that they actually, Mikowski and Bada made photographs, and they were actually able to photograph it based on some very accurate positions that were provided by radio astronomers. And this Cygnus A galaxy was not in any catalogs that the optical astronomers had published. They completely missed it. It's completely obscure and not very bright. So here is this galaxy that's the brightest galaxy that we know of, and produces the most energy. And we can't even see it with it. Very hard to see with a telescope. It's really far away, and so it's putting out a tremendous amount of power. Here's a radio map of the Cygnus A at 20 centimeter wavelength. I think these maps are and you can see there's two of them. There's two big radio lobes, and Cygnus A is between them. Here's a picture of Cygnus A. This is what it looks like. This picture is is not very clear as to what it is. Can you see what it is? I can't really tell. Anyway, the speculation was that because of the early pictures, that this was two galaxies colliding, and this became a very popular explanation for radio galaxies, was that there are two spiral galaxies and they're just smashing into each other, and when they're smashing into each other, they're producing all this radio wave energy as a result. Okay, now I'm going to talk about, does anybody have any questions about that? I'm going pretty fast.
How can you tell they're colliding?
Excuse me?
How can they tell they're colliding?
Well,
Stop photograph.
it turns out that that theory went by the wayside pretty early. But,
Okay.
But it's interesting. I just brought that up because that's still a popular theory. Okay, interestingly enough. Okay, I'm going to talk about Virgo A, which is really quite interesting, also known as M87. This is probably the most thoroughly studied radio galaxy. I could probably talk about this for quite a long time. It's an elliptical galaxy located in the Virgo cluster, and that's a well-known galaxy cluster in the constellation Virgo. And this is kind of interesting. Here's a picture of it, and it's not a double radio source. It's when they first started looking at it, it looked to them like it was just a elliptical source. You could see here in the center, with these better techniques than we have today, we can see a lot of structure. So what this source is, and it turns out that the center, there's more detail in the center. So what you have with these radio galaxies is you'll have like a halo. You can see here's a halo surrounding it. Then in the center you get a bright center. And then it turns out they can resolve detail in the bright center. Okay, now here's one of the main reasons for bringing this up. This particular radio galaxy is where they got this picture of the supermassive black hole that was published a few years ago. And there's the picture. What is it a picture of? It's a picture of the center of M87.
It's a torus field.
Could be, might not be. It's poor resolution. I want to talk about Centaurus A. This is another pretty interesting radio source. It's got you notice that Virgo A had a designation M87, which meant it was in the Messier list, and that was a list published in the 18th century, so it's pretty bright. It was a pretty bright and well-known galaxy. They didn't need to discover it with a radio telescope. Centaurus A is another example of that. It's in the NGC catalog, New Galactic Catalog, so it has a designation. And it's a pretty bright galaxy. It's pretty close to us. And it turns out Centaurus A is actually the closest radio galaxy to the Earth. And it's also a bright double radio source. So it has two large regions of it's the closest radio galaxy. And this is another example of a galaxy with multiple structures. This is what it looks like when you photograph it with the telescope. It's oops, shouldn't have clicked on that. It's looks like an elliptical galaxy, which is elliptical or circular in shape, spherical, ellipsoid in shape, and then it's got this dust band across it. This makes it kind of unique, so it's classified as a peculiar elliptical galaxy. Here's this kind of interesting. When it's looked at different wavelengths. It's got a big halo. It's got a big optical halo. Whoop, moved it again. It's got a big optical halo. You got the dust band. You've got this radio emission spouting out both ends of it. Okay. This is a picture of the X-ray jet that's coming out of the center of it. It's kind of interesting. This is an X-ray. This is what the X-ray jet looks like. Interestingly, the jet only points in one direction. There's not a counter jet in the opposite direction. Okay. Anybody got any questions about that? It turns out, I could talk more about it if you want. Okay, here we got Hercules A. This is kind of an interesting one. This is another one that they didn't really notice that it's not a very bright galaxy. Didn't really come across in the when the optical people were doing surveys. They didn't pick it up, and it was basically because it's a strong radio source that they started looking for it and then identified it, and it turned out to be another elliptical galaxy in the center of a cluster. So it's not that bright. It's also an X-ray source, and here's a picture of what it looks like. This one's kind of interesting because it looks like it's got two nuclei. Not really clear whether this is a galaxy that's split. Its nucleus is split, and it's released a baby galaxy. Could be. Some people would argue that, well, that's just another galaxy in front that we're just looking at it. That's the traditional view of it. Here's
Or
the picture. Here's the picture. It's a double lobe radio source. And I like that this picture is kind of interesting because it looks like it's blowing plasma bubbles out, particularly on the lower right side. You can't see that very well in the upper left side, but it looks like it's, and you see that there is the classic double jet structure. It's squirting plasma or whatever it's squirting out of both sides, as opposed to, as I pointed out before, sometimes
Electrons. It's spitting out electrons.
Sometimes the jets aren't symmetrical. This one has the symmetrical jets. Here's another one that's good, Perseus A. And this is another galaxy that's very peculiar, and they don't really know how to classify it. They call it a Seyfert galaxy, so it's included in Seyfert's list of galaxies. Seyfert galaxy is a galaxy that has emission lines in its nucleus, and normal galaxies don't usually have emission lines in their nucleus, so that's one of the characteristics. But this one is, it's also a radio source. Some Seyfert galaxies are radio sources, not all of them. And again, it's near the center of this Perseus cluster, and some people claim they're two galaxies. It's really two galaxies, one in front of the other, and they may be colliding. There's that colliding galaxy idea again. Okay, so Perseus A is on the left, NGC 1275 is on the left, and it's not really a classic, like in Hercules A. See, Hercules A, you could see there are clearly two distinct radio lobes, and Perseus A, it's kind of, not really, maybe you could sort of see there, it's not what you would call your classic double source. Now these other two are also in the Perseus cluster. This one here in the center is NGC 1265, and it looks like, and probably can't see it too well, it's squirting out, it's got jets on both sides of it, and it's squirting out radio emissions. And the radio emissions are falling behind, so the theory is that it's moving through the cluster, and that the gas in the cluster is essentially kind of like it's like the galaxy is moving through the atmosphere, and it's leaving this smoke trail. So it's like it's got two sources that are squirting, and as it's moving along, it leaves them as a trail behind it. And that's their explanation. That's kind of an interesting morphology. Then this one on the right, IC 310, all you have is one trail. You don't have the classic double structure. So here you have three different radio galaxy structures. You have the one in the middle has got jets coming out of both sides of it. The one on the left doesn't seem to have any jets at all, and the one on the right seems to only have one jet. So it's kind of a mixed bag. This one I like. This one's kind of interesting. We're getting towards the end here. Fornax A, it's another one of these elliptical galaxies. There's a picture of it. It's got this dust. Elliptical galaxies aren't supposed to have dust. It's got all this dusty stuff. And if we go back to NGC 5128, you see there's dust here. There's a lot of it in that one, and not so much in this one. So it kind of suggests that maybe this is not as evolved as Centaurus A. Okay, here's what it looks like in the radio frequency range. These orange areas are radio emission. This thing is huge. This is the Galaxy Fornax A. It's huge. I mean, it's big, and it does have the classic double source, but it does. You don't see any jets squirting out, and they're just big blobs, and they're pretty close to the optical extent of the galaxy. So this is another, looks different. It's not okay. So we're coming up to the end here. We only have, well, I guess we got 8 minutes. And the main part here, this is, I didn't really get a chance to do much work on this, but I pointed out the black hole. We had the picture of the black hole. There's the black hole. They've essentially refined this picture, make it look more like it's a ring and a black hole in the center. So the theory that, and I didn't really talk a little bit about Slavovsky. I can't really pronounce the Russian guy's name. And they, towards the end of the 1950s, came up with this theory of synchrotron radiation. And that's been the primary explanation for what causes this radio emission from galaxies. And one of the reasons is that it predicts that the radiation would be polarized, and they've done experiments, done measurements, and they do show that the radiation is polarized, and so that supports the synchrotron emission theory. Now, what is producing this? The current theory is that there's this thing called a supermassive black hole, and you know, to me, it's kind of like, well, you don't have an explanation for what this thing is, and so you've got this black hole theory thing that really doesn't have a whole lot of experimental tests behind it, because it's cosmological speculation. So they matched the theory to the observation. There's a problem with the supermassive black hole theory, in my opinion, which is, where do these things come from? Black holes are supposed to form, it's a star, and then it gravitationally collapses, and then it sucks in all this gas from around it, and as it's sucking in all this gas from its surroundings, creates what they call a accretion disk, and this accretion disk is supposed to get really hot and radiate X-rays and all these exotic high energy emissions. And so that's their theoretical explanation. And then supposedly the black hole shoots jets out in opposite directions from along its axis of rotation. I can't really say much about that now. I haven't really studied that theory very thoroughly, but it's seems kind of not really convincing to me, but I guess if you're an expert physicist, it might convince you. And of course, at the bottom, we have that this hypothesis is not falsifiable because, you know, we're not really close enough to any of these objects to really make measurements on them. I'm not really convinced that this picture is I don't, you know, they claim that's a picture of a black hole. Well, who knows? All right. Any questions before we got about 5 minutes before the end.
Well, is anyone here familiar with Ron Hatch's many patents and how he says that, you know, the disputes relativity, special or general or both? Ron Hatch, he has many patents with GPS. I don't know if anyone's familiar with him, because some of the mainstream people in the chat room on the science shows claim that he's a fraud and such.
Well, of course. Why wouldn't you?
Oh yeah, I know.
Yeah, well, that's another subject. But I think, like Kev, for example, on the chat show, a lot of people, you know, are saying Ron Hatch says this and Ron Hatch says that, and he just put in a couple of comments. He said, "Well, I've done a bit of research on this, and he's nothing. He's a bit of a fraud, and so on." So I think it was a bit of a backlash. I don't know, because Kev is a fairly orthodox physicist, as far as I can tell, and there are one or two others as well.
Well, part of
why I brought that up though was because well, it's related as far as supermassive black holes. I mean, maybe it is densely packed mass, with high gravitational strength. I mean, that doesn't mean that it slows down time. That there's no time relative to an outside source or very slow time. That's just one point there.
Were you here for the previous where I talked about this? You weren't here for the first.
Oh, you mean today?
Yes.
Oh no, I tuned in late.
Yeah, well, I'm sorry. I don't know that I want to go over it again. My point, the issue in my mind is that in our first session we discussed why there's lots of problems with the interpretation of the LTs and relativity. And now we have that, if you take this theory to its ultimate, you get a black hole, and now they're saying that this thing that's a theoretical construct, black hole, is an explanation for all these real physical phenomena. Okay, it's a black hole is at the center here, and it's squirting out all this energy that's creating these radio loads. Okay, that's the theory that they're promoting. Here's the picture of it. I don't see a black hole in there, but anyway. Here's a Virgo A. It doesn't even look like Cygnus A. I mean, Cygnus A is a double source. Virgo A doesn't look like it. This is what the that's something different. That's a donut with a hole in the middle. That doesn't look like
the black hole, simply a lady tinkering around with graphics on a computer.
Could be. I think it's a case. It could be. I don't know what this is. I mean, it's not an accretion disk. This is the thing. Where's the accretion disk that's supposed to exist? There's supposed to be and I didn't really get to the point in this presentation where I went into the physics of black holes. I just I'm actually only at the stage where I'm talking about what do these things look like. In my opinion, I talked about this previously about a month or so ago, where I showed a picture of the here's one. Well, it's this picture here. According to the theory, the black hole is supposed to point perpendicular to the dust, but here the jet is coming out at an angle. So why this doesn't confirm? Plus, there's nothing on the other side. The jet's only coming out on one side. It's not coming out on both sides like the theory predicts it's supposed to. And why is it that some radio galaxies, they're this classic, that's a classic double radio galaxy. Here's another classic double radio galaxy. But here on the NGC 1275, it doesn't really look like the classic radio galaxy. Here, the one in the center doesn't you could sort of argue, but that doesn't really look like the classic example.
Imprinted upon that. In other words, they made the image to conform to their theory.
Right. Well, I think that's really kind of what it is. The theory is dominating the interpretation of what is observed, and so that's kind of the issue there. And my point is, there's so many differences for these different galaxies. They don't look the same. There's some similarities, but they don't really look at all the same. Each one of them seems to be unique.
I sense, though, for maybe the first time, they're suggesting that the James Webb telescope results may need them to revise their theories very much. Perhaps, for example, that they may need to double the supposed age of the Earth of the universe since the Big Bang to 26 or something. Hey, this is what they're saying now, but they wouldn't.
Well, they're nice. They're going to hold on to their pet theories as long as they can. That's a point that Roger keeps making. What ad hoc modifications can we put into the math model that keeps our basic premises intact? And right now, the basic premise is that black holes are at the center. A supermassive black hole is at the center of every galaxy in the universe. That's whether it's a radio galaxy or not. There's a supermassive black hole at the center of the Milky Way. Every galaxy has a supermassive black hole at the center of it, which, that's become pretty much mantra now.
Harry, you mentioned that the spectrum is one thing that folks are looking at. Is there any information that you've come across that indicates the mechanism for the particular spectrums emitted?
Well, that's another mixed bag. I mean, you could spend write a whole book on that subject. As I was just pointing out, they look different. The spectrums are different too. So, you look at one galaxy, they all have different spectra, and it's very tough, to make a claim that you can explain all these phenomenon with a one theory fits all type of thing. That's my kind of the point I'm getting at. Their working assumption is that all galaxies have supermassive black holes, and then that becomes a explanatory device for everything. Okay, you see what I'm driving at?
Yeah, but in terms of just spectrographic analysis, what atoms are emitting this radiation, like you mentioned, neutral hydrogen, would be of interest.
Well, this is a big subject area, and I only touched on a few of the basics at the beginning, and I sort of went through it pretty quickly because I wanted to squeeze it into a half hour.
Understood.
The real point is that Slavoski, and I'm not really sure I'm pronouncing his name correctly, but I have a copy of his book. He, towards the end of the 1950s, proposed this idea of synchrotron radiation, which is that high energy electrons and protons and whatever are spinning around in these magnetic fields, and they emit this synchrotron radiation, which the reason it's called synchrotron is because it was observed in particle accelerators. And so the theory of synchrotron radiation comes from the particle accelerator theory, where this radiation was originally observed and explained. And I don't know, I think they're still holding on to that theory. And I don't know that I'm convinced of it. I'm not sure I'm convinced. I find it hard to believe, if you go back to these pictures, these. Okay, here's a good one. This is Hercules A. This thing is way out there. This thing isn't close. It's not close to us. The amount of energy that this thing is putting out is tremendous. It's mind-boggling. It's like 10 to the 50 something watts. 10 to the 50 something. Yeah, I mean, it's a mind-boggling amount of energy. And look how it's collimated. It's squirting it out in these jets, and then it's expanding like these are big bubbles or something. I don't really see how, you could be shooting out all these particles, these electrons and whatever, and they're spinning around in a magnetic field, but the size of the magnetic field you would have to have is huge. It's just, to me, the whole thing is just, it's mind-boggling, actually.
What is it exactly that accounts for why some areas are more prominently brighter than others?
I don't know. I'm not an expert on this. That's a good question. The assumption is there's more power coming out. In one respect, you could interpret this as this is like a water sprinkler, and it's rotating, and the left part looks like it might be approaching, and the right part looks like it might be receding. It's kind of hard to say. It could be the opposite. Some of the maps are a little better than others. This one doesn't really help. Is the lobe on the left receding, or is that brighter because it's approaching us? Maybe the one on the right is moving away. It's kind of hard to say. Some of them, in some of the maps that you can see in Centaurus A, which is closer, it looks like this part up here on the upper left, you see this part, looks like it's trailing back. The radiation is like, so it looks like that the galaxy is rotating. The upper left part is rotating towards us, and the bottom right part is rotating away. That's just what it looks like to me.
Does the red areas, does that
the red is this red area here. Can you see the cursor? This is the radio part.
And then there's some very bright areas right there in the middle. Well, I mean,
this is the optical picture, and then on the optical picture they've superposed the radio map, and also there's an X-ray inside here. This jet here, right here, that's pointing off to the upper left. That's part of the X-ray emission that's detected.
Okay.
And
that doesn't point to the red shift. I mean, is the red shift detected? Does it literally look red, or is that just a term they use?
Well, you can't determine redshift from the radio maps.
So it may look red, necessarily isn't receding.
That's just a color that they chose to represent the...
It's a range of emission, man. It's a color.
All right.
Okay.
This is a multiple... the red is just used to represent the radio emission at a particular frequency. It doesn't represent anything. And then there's an optical map. And this is kind of interesting in that the reason it's here is because it shows that there's different phenomenon at work. You've got radio. It's visible in the radio frequency range. It's visible in the optical range. It's visible in the infrared range, and it's also visible in X-ray range. So it's multiple ranges of frequency this thing is visible in. That's pretty interesting in and of itself.
So,
why is it?
So each each area of the electromagnetic spectrum, they pick up something that all the others don't, or is it typical that more than one picks it up, any given galaxy?
Well, it's radiating at this tremendous range of frequencies. It's radiating at radio, it's radiating at infrared, it's radiating
X-rays,
optical, and it's radiating in X-rays.
Well, what I meant was, I mean, has any galaxy or area of space been discovered where only one or very few pick up something?
Yeah, there are examples of that, I believe. This is all part of the puzzle that these people are working with to try to solve. And, there's a lot of, each object that you look at is kind of unique. The reason this Centaurus A is significant because it's the closest radio galaxy. And even before, it's had this, optical astronomers, they didn't know anything about radio or anything. They could still see there was something strange about this because of this big band of dust here. This doesn't look like any other galaxy. It's kind of unique. And so what they do is they put this term peculiar on it. They call this a peculiar elliptical galaxy because you take away the dust, you get an elliptical galaxy. One of the main things about all these galaxies that I'm talking about, they're peculiar in some way or another. Okay. Here's Fornax A. I mean, it's got all this dust. It looks like an elliptical galaxy, but it's got all this dust. It's not supposed to have all this dust. Elliptical galaxies don't have dust, so they all call it peculiar. Okay? It's peculiar.
In order to calculate the amount of energy that these things are supposed to be giving off, they're presumably back into the same sort of quandary as for optical astronomy. In other words, they're estimating the distance away by observation, by Cepheid variables, and then they're using things like Hubble laws. Is that presumably the case?
Yes. Now, most of these are too far away to calibrate by Cepheid variables, so they're basically using the redshift. So they measure the redshift at the optical frequencies, which is an absorption line or an emission line, usually in the nucleus if it's bright enough.
So there's the problem that just as they're estimating huge, really huge absolute intensities of these objects very far away because they've used this so-called linear Hubble law, they're quite possibly estimating huge amounts of energy, as you say, being given off, which are perhaps overestimated because they've used this simple Hubble.
Right. I didn't talk about quasars. This is where in the 60s when they discovered quasars, okay, which was when they were picking it up at the radio frequency, and then when they looked to see what it was, when they got a close enough idea of what the position was, all they saw was a star. Okay, and at this time, the radio star, you notice I mentioned earlier that they thought these things were radio stars back in the late 40s, early 50s. They were talking about radio stars because these are discrete radio sources. Okay, meaning that they're point-like or they look like stars. Okay, then when they started identifying them with objects in the galaxy, supernova remnants, that sort of thing, and external galaxies, the idea that stars produce radio emission kind of fell into disfavor, although stars are detected to do produce radio emission. We know the sun does. And I'm kind of losing my track. Okay, anyway, when they discovered that these quasars were stars, okay, so you have the famous case of 3C 273, it's this star, okay, it looks like a star. What is it? It produces radio waves. And then when they measured the redshift, well, actually, they didn't know what it was because when they measured the spectrum, they couldn't figure out what the spectrum was until one fellow realized that the spectrum was really significantly redshifted. And from that, they produced these estimates that these things are really, really, really way far away. Okay? And the power that these things must be emitting is just tremendous. And this caused a big problem in the 1960s. How to explain this. And this is really where black hole, supermassive black hole idea started to come into the picture. It was proposed that these are black holes, that quasars are black holes. And that, because they couldn't imagine any other way of producing the amount of energy that these things are radiating. It's just a tremendous amount. And so the only way they could figure that out was it had to be this really, really, really big black hole. But on the other hand, this really, really big black hole has to be gobbling up all this matter. It has to be gobbling up stars and gas to produce all this tremendous amount of energy. And when you look at a quasar, you can't see anything around it that it could be gobbling up. Well, they found a few that they now claim that explain that quasars are gobbling up other stars and that surround them. But, to me, it's all still kind of flaky.
I have one question only. What about fast radio bursts? What can you say about it?
I haven't gotten to that point where I can say anything about it. I've read your papers, and to me, it looks like a new type of phenomenon that's of recent discovery.
Recent discovery, you're right, about 15 years old, only, not much. But what is important, these sources are about 1 billion or even more light years from us, and we can measure this fast radio burst now. Can you imagine what is the power of this burst? It's unbelievable. It's much more than you discuss right now. That's why it's not only this, radio sources what you talked about, but fast radio bursts, much higher power, and they cannot explain it at all. And what is important, there are no the black holes, forget about them. Because what kind of black holes we have with some jets out of it? Come on, it should swallow all the matter around. There is no way to eject something, man. It's against logic. The meaning of black hole, it will take all the matter around. But on the contrary, there is some source of energy out of the black hole. Come on. Forget about this explanation. It's absolutely wrong.
I have to admit, I'm sympathetic to that point of view. I don't understand how a black hole shoots stuff out. It's supposed to swallow stuff. So stuff is supposed to go into the black hole and not come out.
Yes. And what is important, even in our galaxy, astronomers already found the star that was shooting exactly from the center of our Milky Way galaxy with supermassive black hole. They proved it, they confirmed it. I referred to this paper, and it's enough. It's only one star, enough to show that there is no black hole inside of our galaxy. But what is important, even how to arrange the black hole, you must have a huge time, first of all, to generate some galaxies, then to have some instability, then you will swallow it, and so on and so on. But our galaxy, Milky Way galaxy, exists at least for 13.6 billion light years, or billion years. And this universe, 13.8 billion years. For 200 million, you must create all the galaxies. Then you must absorb them all together and to arrange this, black hole. Forget it. There is no time for all this process. That's why black hole is a mathematical trick only.
I think this is an example of, in physics, in the way they're doing science, they can't admit that something's unexplained, and because they can't. They just can't say, well, we don't really know what causes this. They're physicists, so they have to explain something, and so then they have to explain it using known physics, and known physics I don't think is really adequate. And instead of saying, oh, known physics isn't adequate to explain this phenomenon, they just try to explain it with ad hoc explanations.
It's not, because it's against logic, man. No, I'm so sorry. Yeah, I'm so sorry. Even by definition, what does it mean, black hole? That's it, simple like that. By the way, let me remind you that in our galaxy we have Fermi bubbles. There are two bubbles, huge one as the size of our galaxy, and they look like the bubbles you showed on some pictures. Sample, but there is no explanation of it even for Fermi bubbles right now, close to us. What are you talking about? Some very far away, all these bubbles, and so on and so on. Man, I don't know. Let me ask you the question. You told that there is a radio emission of hydrogen. It's a molecular hydrogen or atomic hydrogen. And what was the wavelength or frequency of this radiation? Radio radiation from hydrogen.
It's a neutral hydrogen, and it's a molecular transition, as I believe. I can't say as I'm a big expert on this. I didn't really go into this, into that question. That's 1950. That was when, and I can't, Van der Hulst, I think was the guy's name, a Dutch guy, came up with this theory of this neutral hydrogen emission. And the frequency is about 1.4 gigahertz, I believe. And there's this conflict. It's kind of the same frequency that is used by GPS. And the radio astronomers, they got into a conflict because the radio astronomers got this frequency range privileged. You're not supposed to use any satellites on that frequency range, and the navigation satellites decided this was a good frequency to use. And when I was working, they asked me to do a study of this, and I gave them a rather unsatisfactory report that said that this was going to interfere with radio telescopes, and they didn't like that answer at all.
Yes, you're right. You're absolutely right. What I mean, right now it's a very popular 21 centimeter radiation, radio radiation, 21 centimeters.
That's around 1.4 gigahertz, as I recall. Right, 21 centimeters. Yes, that's correct. I was looking for that. I don't remember it off the top of my head. Yeah, 21. Now, what they do is they measure the frequency they measure the Doppler shift of the frequency, and that tells them, they can identify what spiral arm of the galaxy they're in, that sort of thing. I'm more interested in the extragalactic stuff, so I didn't really look at that very closely.
It's impossible, man, to take in half hour, in 1 hour, all the experimental results what we have in radio astronomy. It's absolutely impossible.
Well, that's why I call it introduction.
Yes, it's a history. That's exactly what I like in your presentations. I watched, by the way, your microwave background radiation. I found so many news for me from history of this discovery. Oh my goodness. You're a historical guy. You know how it started, how it was proceeded, and where we are right now. This the most important part of your presentations. Knowledge about the discovery of something very unique from the very beginning, because most of our orthodoxies, they know nothing about the history. This is the main point of your and mine. Let's take a look back in the time. Find what was the beginning of the story, how it was developed, why we came to these ideas right now. It's very, very important for students like ourselves for radio astronomy. But I don't know too much about them, and I'm very impressed with your presentation and history of all this continuously discovering in radio astronomy.
Well, this is in my real. I'm a radio engineer. And you notice that Grote Reber, I'm so impressed by Grote Reber. When I first started doing this, I got completely absorbed in trying to figure out what equipment Grote Reber was using. And I also got into Jansky's equipment. What was Jansky using? What electronic? What was his antenna? I couldn't figure out what the antenna was. And you show the pictures, and you can't really. It's a bizarre-looking thing. What is that? And so this is kind of, to me, this is interesting. I don't know that anybody else is interested in Jansky's antenna is a Bruce array, rotatable Bruce array. I could lecture for an hour on what a Bruce array is.
Okay, you know what? History of physics, it's what's missed right now by most of orthodoxies. They know nothing about it. Supposedly, dark matter, everybody told. It's Zwicky who proposed dark matter. Forget it. John Mitchell, 450 years ago, before him, far away before, he proposed these dark stars. I told about them. You see, I opened for myself the history of physics. That's why I'm so happy with you that you gave us another picture of the history of classical physics. Thank you so much for this.
Okay, Jerry, do you have any questions? I'll bet you do.
How exactly do they detect noise in outer space, like in distant outer space? Because sound needs a medium to travel through. Is it within extremely local areas where the mass is densely packed, in any given vicinity?
Well, I'm not sure what you're asking. I tried to
how they detect sound or noise, because sound requires a medium. I mean,
we're talking about radio waves here.
Yeah. Well, it says that radio waves detect noise. Does that mean sound?
No.
Oh, okay. I'm sorry. I understand.
That's a terminology issue.
What does noise mean, though? Then?
I defined it. It's maybe I should not have skipped over this part as fast as I did. Essentially, what the term noise means, and I tried to define it. It means when your radio, you're trying to communicate. This is like what Jansky was doing. You're trying to communicate. You're trying to receive a signal from a radio station, and there's noise that's interfering with your hearing the radio station.
Yeah.
Okay. And so Carl Jansky was investigating where noise could come from. And if you read, I looked at his report. They were mainly interested in, is it noise coming from, down the street? That's a problem. Today, noise coming from down the street is a big problem. But he, which I thought was kind of interesting, he determined that a lot of the noise was coming from thunderstorms. And he talks about the thunderstorms and how much noise the thunderstorms generated. But those were not very, a thunderstorm would come up in the day and then disappear, and at night they didn't have thunderstorms because, mostly in the summer you have thunderstorms during the day. But he kept detecting this noise source that, would appear on a time of about 24 hours, and then eventually discovered that it was a sidereal time. In other words, it was correlated with the rotation of the Earth. And there was a noise source that would appear, and then disappear, and then come back the next day, and it would be shifted in time by 6 minutes. Okay, and that's the difference between a solar day and a sidereal day. And so he deduced from that it was coming from an external source.
Okay, let me give some comment. Noise means broad band radiation without any peculiar lines or something real. It's all the wavelengths at the same time. This is a noise. That's why you cannot tell anything about who is the thought, who is doing this broad band noise. Sometimes it's named black noise, means there is no any lines. There is only homogeneous radiation in all their wide band of radio waves. That's why you cannot tell anything about it.
I didn't. I probably should. Yeah. The issue is that there's lots of different types of noise.
Yes, I told about the black noise.
You're describing radio hiss, and galactic noise is usually pretty well described by that. But you also have lightning noise, which is this big burst of noise in time. The noise, it's just a bunch of noise, and it comes up and it goes away. And
something random. Something random. It's not. Yes, I'm sorry.
So I use the word here in the beginning, studying atmospherics. In the early reports, they call these things atmospherics, which really means lightning noise, I think. Noise that's created in the atmosphere. Lightning is one example. I think there are other sources. And this term static is used in the literature. Generally, we don't use the word static anymore. Okay.
I know. But might be
engineers, if they said, I have this static, that's not a term that's commonly used. That's an old term for noise. Crackling noise. And I think in the older receivers, the noise had this crackly sound. It didn't sound like white noise or the noise, what you would call like static noise today. It kind of, because the speakers were pretty bad and the audio circuitry was really awful, it came out with this crackly sound. And I think that's where they got this term static comes from. I think static electricity. I tried to figure out where this term static came from, and it seems like nobody really is sure where this word static noise comes from. Lots of thoughts about that.
Maybe this is static noise from ionosphere, because we have ionosphere, we have a plasma, we have some fluctuations inside of this plasma, and then you have your radio waves from our ionosphere, and that's a simple exist for me, because I'm not expert in your business at all.
Well, being an amateur radio operator, I can tell you that there's all kinds of noise. Okay, and noise being defined as something that interferes with your communication. You're trying to hear the guy in the other end, and there's all kinds of noise. There's the lightning noise, which we call QRN, and then there's a noise on the antenna. And there's an antenna noise that is called is kind of a static noise, and those noises aren't that, the QRN noise, the lightning noise is really bad. I mean, if you have a lightning storm nearby, it's overwhelming. But nowadays you have computers, TV sets, and all these things, and cars, automobiles, and there's just all this noise. They produce all this noise and interference. And so there's all these different types. And to a certain extent, that's what Jansky was doing. He was going like, where are these noise things? I got all this noise in my receiver. Where is it coming from? And he was trying to figure that out. And I think he was more interested in the noise that was coming from the atmosphere, because they're sources of atmospheric noise. And the main sources that he talks about is the lightning noise and then this cosmic noise. And Reber calls it cosmic static.
Confusion might have been that in everyday parlance, noise means something audible, just audio frequencies. But here it can, traverse all frequencies.
Well,
and
radio
of course,
engineer doesn't think about it as being audible.
right. But when you get these electromagnetic radiations being heterodyned, well then it can be picked up as audible noise on, say, a receiver.
Well, on the receiver, it's audio noise. When you listen to it on the receiver, it's noise. It's like what Jerry was saying. It's noise. I mean, it just comes out as a bunch of noise on the receiver.
Right. Even though the origin of it is not audible.
Yeah, it's being picked up by the antenna. And one of the things in ham radio that a lot of people talk about is one of the technical issues that is confusing to a lot of people, and that is, how do you track down? You got noise. You're hearing noise. Where is it coming from? How do you track it down? And there's lots of different opinions about how to get rid of it. How do you suppress it? How do you what are the methods or the techniques to get rid of it? And it turns out that's a big area of discussion. You get into ferrite beads and coils and all kinds of technical gimmicks that are used to get rid of the noise. And the noise comes from everywhere. Car driving down the street, the next door neighbor's TV set, all this, it's all noise. Jansky had it easy. He didn't have to worry about noise from computers and TV sets and all that other stuff.
It's something random. We don't know where it's coming from.
We have stricter regulations now about suppression of interference. Years ago, if your neighbor put on his vacuum cleaner, it would upset your radio or television.
Yes.
Yeah, and I can tell you a story about that. As when I was working as a satellite engineer, we had this procedure where we'd have to do a 24-hour test. And you'd put a bit error rate detector on the satellite link, and the link was supposed to run for 24 hours error-free. And this one station was in Germany, and we had a station here in the United States. And every time we tried to do the test, it would fail. But it would always fail at the same time of the day. And what happened was they discovered that the janitor came in at 12 o'clock and plugged in the floor buffer. And every time he turned on the floor buffer, the satellite link went out because he plugged the floor buffer into the equipment rack where the receivers were. And so the buffer noise went up into the receiver and wiped out the